All right. Hello, hello, hello. Good evening, good day, good morning, good afternoon, good night, wherever you are in the world again. Well, it's evening here, and welcome to another stream for Freaky Physics. For today, we have a lesson. We have CJ again on board, and well, for those taking the IB exams for physics, that's tomorrow. So good luck to you. And well, we still have some time, and CJ has joined us. So let me bring him in. Hi, CJ. You there? Good afternoon, or good evening, rather. Okay. All right. While waiting, let me just set up the board here. Oh, I'm not wearing my lab coat. Where is it? Oh, here it is. Right behind me. Hmm. But okay, I gotta pick comfort or look good. Most people would pick look good, and so do I. At least for the stream. Anyway, this lab coat's got a short sleeves. It's really hot right now. What I've done is I've turned on the air conditioning and then but the air conditioning isn't in here in this area of the house. So I just turn it on and I have the fan on to blow some cold air from the AC. All right, let's see. CJ, are you there yet? No, not yet. Okay, so while we're waiting for CJ to come in, uh, let's open the board. Ah, here he is, I think.
Hi, residents.
Hi, CJ, how are you?
Sorry.
Sorry, sorry. All right. Can you hear me now?
Yes.
All right, great. Ready for tomorrow?
Not paper one. Maybe paper three. Paper three was good. Will be fine.
Hmm. Most people will say that for paper three. It's relatively
But it
easy.
doesn't work out.
Well, no,
Oh.
actually, no. I would have to say, yeah, paper three is for the most part relatively easy if you get to prepare for it properly.
Oh.
Basically, yeah.
I
And what's the
think
proper part of it? The proper part of preparation is one of the parts for preparation would be the what's this? The section, the data analysis section, right?
Mm-hmm.
Uh-huh.
Oh yeah.
Okay, so if you prepare well for that and you studied well enough for astrophysics, you should be okay, or whatever option you're doing. Okay.
hmm
Uh,
Um.
Go
Wait.
ahead.
Do you know Revision Village?
Yeah, I've heard about it and I've seen some
Do you have
papers. Yes.
Do you have like would you recommend using their prediction exams?
I've never actually tried the prediction exams.
I'll
I've
give you a question from there.
All right, sure, go ahead.
I'll screenshot it and send it
Sure.
here.
Okay, hold on. Let me refresh the board here as well because it's not loading. Okay, let me check the thing. Okay. All right, let me see the screenshot. I'll just check the question itself first. If this is the first question, probably I'm not so sure, but probably
Okay.
right.
As
I would
yeah.
I would rather see some of the questions from the other sections, not from topic one, because topic one's basically too general to actually give a prediction. But if you give me like topic
Mhm.
three or topic four questions, that should give me a better estimate.
Topic four, sure.
Right.
Um, let me find topic four then.
Okay. Oh, I see
There's
it.
a lot of wave graphs. But
Yeah.
oh, here's one.
I see one. Okay, I see the topic 2-1. Ball is projected, your existence is ignored. You're given the path. I wonder what's wrong. My Ziteboard isn't loading much in this case. from my side. Okay, I'll just refresh
It's
the whole
weird.
thing.
Maybe the server is down.
Yeah. Hmm. All right. So anyway, okay, the question is loaded. Honestly, this feels more like an A level question rather than an IB question.
Okay.
Yeah. But more or less same difficulty, so should be fine. So that's the projectile question. Let me look at the okay, this question about the blocks or the boxes, the 7 and 3 kilogram box with the force on it. Um, Possibly this could be a good
Hmm.
indicator. Right, next one, the waves. The first one about waves. Okay, okay. Okay, two water waves there. Water position is at equilibrium is at 5. Maximum minimum water levels when the two waves overlap. Okay, possible. This question about the water waves is possible, and the last one about the light, right? Yeah, beam of light. Possible as well.
Hmm.
So this would give you it's not gonna be perfect, but it's still a good indicator. So yeah, so if you want to take that revision village questionnaire and see what you would get, go ahead. You can do
Okay.
so. All right.
Yeah, they have like a full like paper one. It's like 30 questions
30
exactly.
questions. Okay, great.
They have paper
Um,
two and paper three as well.
mhm. Well, okay.
Wait, do you know if the exam's in the morning?
Uh, Hold on. If I'm not mistaken, they're in the afternoon tomorrow.
Yeah, I think so too because I'm looking here and it just says PM. It doesn't
Yeah.
tell me what time. It just says
Oh,
PM.
that normally means because the school or whatever the IB center is, they will the coordinator, your IB coordinator will be, or your DP coordinator would have an actual schedule of times that you can have the exam. Okay, so if it says
Mhm.
PM, it has a range of times where you can take the test.
Mhm. Is it
Um,
1 p.m.? Because
it's usually 1 p.m., 3 p.m.,
start at 3 p.m.?
or 1 p.m. It will depend on which one your school will follow, but
I think it's 1
normally,
p.m.
yeah, normally it's 1 p.m. Anyway, we're on the same
3
time
p.m. is
zone.
crazy.
Yeah, we're on the same time zone, so we would be able to talk about. But of course, we don't want to destroy the integrity of the exam. So we cannot talk about the exam tomorrow. Tomorrow, okay? We can only
Oh, because we're TZ1.
yeah, we're both TZ1, right?
Mhm.
So yeah, we cannot discuss it, especially here that I'm streaming.
Yeah,
All right,
yeah.
so we don't
Oh
want
wait,
to.
we're first.
Sorry, say that again.
We're the first people that take it.
Yeah, more or less. Huh, why am I not able to connect? All right, I think I'll just make a new board because I'm not able to connect to the old board. So
Mhm.
create a new one. I'll call this CJ 24 April. Okay. New public create new. All right. Hope this works. All right. So while we're waiting for the board to load, oh, similarly, one more thing on what's tomorrow? Tomorrow's Thursday. So on Friday, we can probably talk about the exams from tomorrow on Friday. But let's be safe.
Mhm.
Let's just talk about the exam some other time next week, just to be safe.
Sure.
All right.
Mhm.
Okay. All right. So board has now properly loaded. Finally. And why do I have that? Okay. Here. Okay. Okay. The board's ready. Let me just get on here now. Okay. Done. And let's get started. Um, Paper 2 is ready here. Oh, not that. We're not done with the paper
This
2
board
we were
looks
doing
different.
before, right? Yeah, I know. There's that
Yeah.
square, or there's that box there, right? Kind of weird.
Update? Or did you do that?
I think that's an update. I opened the board and it just came out like that.
Hmm.
Okay, football. We're not doing the football one yet. Uh, okay, here. So last time we stopped at. Okay, I think we're ready. So last time we stopped at. Oh, I wonder what this. I think this is something for for us to see where we're writing, so we don't really accidentally change
Go
anything
beyond.
about the
Hmm.
size. All right. So okay, let's start. So I have the question here. So the next question we're going for is about waves. Okay. So here is the first question. All right. And for today, after I just really want to go quickly through these now so that we can cover as much material as we can before tomorrow.
Hmm.
Mhm. All right.
Yeah.
Right. So here we go. So that's the first question. So outline how a standing wave is produced on the string.
Oh, when the okay.
Mm-hmm.
So is the finger pressed on it or is it
It's
like
pressed on it.
moving?
Yes, it's pressed on it.
Okay. So standing wave is formed because where the finger is and where the bridge
Mm-hmm.
is essentially a closed tube
Okay.
is closed.
Mm-hmm.
Therefore, the waves being sent is reflected back and they oscillate.
Okay. All right. So let's take a
Am I
look at.
wrong?
Okay, I think you're right, but I'd rather check the mark scheme here to see how many marks you would get. Okay.
Hmm.
Because
So I talk
in
about
all,
it being in the first harmonic.
yeah, in
No.
okay, hold on. You got two. There are three
Yay.
possible marks, but you got two, and that's enough. Okay. All right. So
There's
what did?
three?
Yeah. There are two marks, but there are three possible ways you can get your two marks. Okay.
Hmm.
So the first statement you said, the first statement you said that you would hold on. Let me double check that. You said something about the wave being reflected, right?
Yes.
Okay, reflected. I'll just say it like this: between the finger and
And the
and the
bridge.
bridge, right?
Hmm.
Okay, this is definitely one mark. Okay, bridge. The second mark here um, would be you have to refer to the idea of the main idea behind standing waves. You have to refer to superposition. So the reflected and original waves, right?
Hmm.
Original waves um, interfere with each other. Okay. Now the third part, I'll just write the third part here just to make it more complete. Okay. The third part here is that the waves interfering, they will only undergo constructive interference for certain wavelengths, right? So they undergo constructive interference um, for for some values of the wavelength only, right? But not others. Okay, so these would be your three marks, and you only need two. So I think you got this mark, and you kind of got this mark, right? Kind of
Hmm.
because of you said reflected in original waves. Okay, so okay. If I was stingy though, I'll give you one.
Yeah.
All right,
I should say the constructive interference one.
yeah, this would be the better answer between among the
Yeah.
three. This would be the biggest part, I think, that would most likely get a mark. Okay, so let's go on to the second part. Okay, the second. Oh, you actually see this? It actually. Oh, this is a nice update. You see that?
Oh, yeah, that's finally much
Mm.
better.
Yeah. All right.
It's exactly what you wanted, isn't it? Because
Yes,
you
it
kept
is.
going down vertically.
Yes, it is. It is. All right. So let's move on. So the string is placed 0.4 centimeters at point P to sound the guitar. Point P on the string vibrates um with a simple harmonic motion on its first harmonic with that frequency, and the sounding length of the string is 62 centimeters. So basically, okay, so basically, if you look at point P here, this is just where you strum that string, right? Okay, show that the
Mhm.
speed of the wave on the string is around 240 meters per second. Okay,
Okay,
so how would we solve
so
this?
V equals F lambda.
Mm-hmm. Correct.
C equals. Wait, let me look at it again.
Okay, you are already
C
given the
equals F lambda.
okay, C equals F lambda. You can actually use V, doesn't matter.
Yep.
Mm-hmm.
So F is 195
Mm-hmm.
times 0.62.
Okay, it's not.
No, no,
Yeah,
no,
you're
no. It, yeah, sorry. It's
mm-hmm.
like the harmonics stuff, right?
Right. It's got harmonics to it, so correct. So C is still C. You're still correct to use 195 for the for the frequency, right?
Hmm.
But what's the wavelength? Okay, remember that the length of the string is 62 centimeters, and you're at the first harmonic.
Hmm. One. Wait, L equals.
Okay, so let's write that here.
Oh, so it's. Wait, is let me think. It's one. No, it's not a quarter of a wave. Is it half of a wave?
Yes, correct. Half of a wavelength. First harmonic, right?
Hmm.
So that means that
There's
will be
2L
2L.
equals lambda,
Okay, correct.
which therefore 0.62 times 2.
Okay, 0.62 times 2. Correct. So that gives you finally,
That's lambda.
yeah, 1 point, well, paper 2, so
2.
you can calculate, right?
Mm-hmm.
Okay, great. So you got the answer already. Just give me the final answer.
242, 2
Mm-hmm.
sig figs. Or, yeah,
Okay,
3 sig figs, I mean.
to 3 sig figs. This is whatever this is, right? And then the final
Mm-hmm.
answer is correct. 242 meters per second to 3 sig figs. So
Yes.
done. Okay.
Um, mm, uh, can you explain to me about the the one
Bless
side
you.
open?
Ah,
Thank you.
okay.
Or
So
like
I'll
how the second harmonic would look like.
okay. I just did this with my students yesterday, and okay, I'm gonna draw it in a way that would not be physically accurate. So again, this is not physically accurate, but it's an easy visualization. Okay. So first of
Mm-hmm.
all, let's say that that's your open pipe or your half open pipe, and it's got a length L, right? Okay.
Mm-hmm.
So remember that the rule that here at the end there must be a node here, and there must be an antinode at the opening, right?
Mm-hmm.
So this is the explanation. So if you have a node and you have an antinode, you basically can have that. Now, this to this, if this looked like a wave, this is one
That's
fourth of a
one
wave.
fourth.
1/4, right?
Mm-hmm.
That's 1/4 of the wavelength. That's why we say here that the first harmonic L is equal to, and I'm gonna write it like this: 1 lambda 1/4, like that.
Mm-hmm.
Okay. Now, if you do it for the second harmonic, and I'm gonna literally do the second harmonic by cutting this in half, right? So if we follow the same rule, that
Mm-hmm.
should be like that. And then this is open. But if this were 1/4, it should go like that, right? But you see a problem here?
Mm-hmm.
This should be an antinode, but we're drawing a node. Should be. Antinode,
Because
so an, right? This is gonna be n. But we have a mode. But position is for node, right? Is for node. So what equation do we get here? Let's just put the equation in just to make it more complete. We get here L is equal to 2 lambda 2 over 4, right? But you will know, but
yeah.
again, because of this, this simply means this will not produce a harmonic. So no harmonic produced because it can't resonate on itself. It cannot interfere on itself and create that resonant frequency, right? No
Hmm.
harmonic produced. So that's why on half
So
open
if both
pipe.
sides are on the same.
Mm-hmm. So okay.
Okay.
So all right. So I think you're kind of seeing a pattern, but I just want to continue just to make sure that this is clear. So if we do that for 3 and 4, I'm just going to do the shortcut now. So if you have this and you divide this into 3 equal bits, you do that, 1, that, and that,
Mm-hmm.
right? And then if you do it into 4 equal
Mm-hmm.
sections, 1, 2, 3, 4 equal sections, we have that, 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 then that. So for n equals 3 and then n equals 4, you
So
notice
four
the
doesn't
patterns?
work
4 doesn't work. 2 doesn't work. 1 works, 3
because it has to
works.
be on different than the start.
So that's why on half
So it's
open
1, 3, 5,
pipes,
7.
yes, on half open pipes, we only have odd harmonics. And what's
Mm-hmm.
the pattern here? Um, what's the L here? Well, we know that that's 1/4 of wavelength, right? So let's just, if we put the drawing here, that's lambda over 4. So that's going to be 3 lambda over 4, right? And let's put 3.
Mm-hmm.
So you see that pattern here? So,
Mm-hmm.
okay. Oh, sorry. So let's do that. So what's the overall pattern? So the overall pattern is the length is equal to n lambda n all over 4 with n being odd numbers, right?
Mm-hmm.
Even numbers don't work. Don't.
Wait, is the n here part of the 4.4?
Yeah.
N1 over N2 equals B2 over
Um,
B1.
this would be if you're already going into the higher harmonics. So most of the time we're doing only the first, right? So in
Mm-hmm.
if we're doing first harmonic, then n equals 1. And that's what you've learned in the syllabus. Okay? So this is a more generalized
Mm-hmm.
case. For closed pipes and for strings, it's the same idea. The only difference is you can have even harmonics and you only divide by 2, not by 4.
Mm-hmm.
Okay? So, okay, I'll just put the summary here on the other side. So again, for uh half open, L should be equal to n lambda n over 4, where n is odd, right?
Mm-hmm.
And then for strings and open pipes, right? Strings and open pipes, the L similarly will still be n lambda n over 2, but in this case, n is any integer, any whole number. Okay, so
For closed and open pipes?
yeah, for strings and open
Mm-hmm.
pipes, also closed pipes, fully closed, right?
Mm-hmm.
Fully closed. Okay, so if it's open pipes, fully closed pipes, and strings, this is the equation. If it's half open pipes, this is the equation.
Mm-hmm.
All right, so let's move on to the next bit here. This time you're given a graph. You're supposed to, okay, let's zoom in now. Ooh, I really love this update. I just saw this today too. Yesterday I was using, I streamed yesterday because some of my students were asking about a few things. So they wanted me to do it on stream, right?
Mm-hmm.
I still didn't see this yesterday. This is really brand new. All
Yeah.
right. All right. So let's go here. Sketch a graph to show how the acceleration at point P varies with the displacement from the rest position. So It's a bit of a trick question because all you have to do here is acceleration and displacement for simple harmonic motion. Okay.
Mhm. On point P.
Uh-huh.
Do I need the
You
graph
don't you don't really need to know that it's point P. All you need to know here is that it is in fact undergoing simple
in
harmonic
rest
motion.
position?
Mm-hmm.
Oh,
So how would
well,
it
if it's
look?
in rest position,
Uh-huh.
then um,
All right.
displacement is 0.
Uh-huh. So here, right? But what
Is it
hap
just a straight line up?
no, it's not.
It's proportional.
Yes, correct. So
Shoot.
remember that A is
So it's straight
proportional
line
to
diagonal.
X, but positive or negative?
Negative.
Negative. So this already tells you what the graph should look like.
Acceleration go up, but displacement's negative. So start
Mm-hmm.
from top left,
Top
go
left,
down.
correct. Okay. Top left, go down, correct. Oh, what just happened?
Or can it start from 0 and go down?
Here's the thing. You have to have both values, so it has to look more or less like this. Okay.
Hmm.
And what's the important thing here? There is a maximum possible displacement. Okay. So this is your
Oh yeah.
okay, and that maximum possible displacement would be the what do we call that?
Um, maximum. Mm,
Mm-hmm.
maximum possible displacement. What do you mean? What do you call? Um. Um.
I think you know.
I don't-
Okay, starts with
Maximum
an A.
possible displacement.
Starts with an A.
Amplitude.
Amplitude. So if we complete the
Yeah.
graph, this is positive A. This would be negative A.
Negative A.
All right. This is the let's just label that here. A is amplitude, right? Okay. Now,
Mm-hmm.
don't worry too much about drawing the amplitude. This is just the safest possible answer for whenever you see this kind of question. If you're graphing acceleration to displacement, add your amplitudes just to be safe. But most of the time, just having it like this, just having
Mm-hmm.
this line with a negative gradient going through the origin is good enough. Okay.
Mm-hmm.
In fact, looking at the mark scheme, let me just check the mark scheme. Yep, this is already correct. You don't have to label your amplitudes
Okay.
according to mark scheme. But again, it's always
Mm-hmm.
safer to mark your amplitudes. Okay.
Well, maybe if it says 2 marks, then we
Yeah,
do it.
if it's 2 marks, you can do it like that. But 1 mark, you don't. Yeah, the amplitudes you can ignore them. Right.
Mm-hmm.
Next section here. Oh, this is gonna be interesting now. We're gonna do a little bit of quantum physics now. Right. Hmm. How's the weather there? Is it kind of improving with the heat and everything, or is it getting hotter?
It's pretty hot. Like right now, my AC is on full blast, and it's still really hot.
Right. For me,
Full blast at 22 degrees, but it feels like
ooh.
28. It's like, well,
Yeah, here the AC here is on as well, and it's on full blast, and I still have a fan on. It's not enough.
well,
All
my
right.
ceiling fan doesn't really work.
All right.
Just waste electricity.
Yeah. All right, so let's go here. So conservation of energy and conservation of momentum are two examples of conservation laws. Outline the significance of the conservation laws of physics. This is a TOK quite type question. This next one.
Uh, um, okay, so can I say without the laws of conservation, not conversation,
Uh huh.
conservation,
Uh huh.
um,
Let
Earth would be kaboomed. Wait, no.
not really. You can't really say that.
We would be sinking underground. Can I say we'd be sinking underground?
We would be sinking underground. No, we can't say that.
We
I
would
want
be sinking through concrete.
okay. Now I want you to kind of think about this in terms of general ideas instead of specific examples like sinking in the ground or
Oh,
concrete. Okay. So
okay. Throwing a ball would. Oh wait, I can't say that.
that's specific. Throwing a ball is specific, right?
Uh-huh.
Okay, I have a
Um,
question.
um,
Right?
mhm.
Just to help you out. Okay. What would happen with all our equations if conservation laws did not exist? With all our physics equations. Can we use them consistently?
No.
No. Okay. That's the key idea here. All the possible answers go to that idea. All the possible answers in the mark scheme, at least, go to that idea.
Mhm.
Okay. So, okay, how would you actually say this in a more specific manner, but still generalized?
Mhm. Um,
Okay. Give me one answer and then I'll tell you all the
without
possibles.
conservation laws,
Mm-hmm.
um, oh, it would be difficult using the physics equations.
Difficult to okay, I think I'm gonna give you a mark for saying that. Yeah. Uh, it would be difficult to solve physics equations. Okay.
Mhm.
I wouldn't personally say difficult. I will say impossible. Okay.
Mhm.
Difficult. Okay, let me just respell that. Difficult to use physics formulas, right?
Mhm.
Okay. Now I'm going to show you what the actual answers are according to the mark scheme in this case. But you will see what I mean when I say this is the key idea once you see all the possible answers in the mark scheme.
Mhm.
There we go. So there we go. Fundamental principles of nature can be expressed. You can model situations, and this would be basically this is the second one. This could also be the third one, right? This could also be the fourth one. This could also be the fifth one, right? So yeah,
Uh,
so in this case, as long as you say something along these lines, it would be difficult for you to do this. Okay, fine, but it would be better to say it in a positive manner. By positive, I mean that the yeah positive manner.
mhm.
Okay, so in this case, what can you do with conservation laws? So not so you'll be able to work with formulas. You can actually just say that. Okay, so conservation laws allow us to use physical formulas or physics formulas to make predictions. My personal answer here would be conservation laws allow us to make predictions accurately. So the way I said it, it's still this one, right? Okay.
Mhm.
So just be careful with the way you say it, but otherwise, I think that's fine. You get the mark. Anyway, TOK question. Usually, it's a bit hard to word them, right? All right.
Yeah.
All right. Let's take a look here now in quantum mechanics. What are the three conservation laws that show that this interaction is possible if you have a pi meson and a proton collide, and then you have your sigma baryon and kaon meson as the products?
Oh wow. Okay. Um, up. So it turns into an up down down. Up up down turns into up down
Okay.
down. Therefore, it
All
is
right.
a neutron. A
Mm-hmm.
proton that changes
A
to a neutron.
proton. Mm-hmm. Okay, I want to ask you something
Uh,
before we continue. Yeah. Uh, Remember in quantum mechanics, we have how many conservation laws? One, two,
three.
technically five, because one
Mm,
of them can be broken into three.
okay.
Okay. But technically five, but yeah, we can say three. Okay.
Okay. So for the first one,
What
an
are the law?
object will stay still if nothing acts on it, and an object will remain in motion if nothing stops it. So therefore,
Ah. Uh-huh.
the first one it collides.
Mm-hmm.
So first one would be uh as it collides. Oh wait, no, that's the third law. Like there's something this. So the force it collides, and then there's an equal force that's set that is acted on the collision on the
Okay.
thing
I'm
that
gonna s-
collided with.
I'm gonna say this now. Quantum mechanics, we don't use Newton's laws.
Sorry, what?
We do
Okay.
we do not use Newton's laws in quantum mechanics because Newton's laws do not apply in quantum mechanics.
Hmm.
They kind of, if the
Oh,
system,
conservation laws.
yeah,
Oh, I read
conservation.
that wrong.
Okay.
Of strangeness, charge, and baryon number.
Uh, you missed one. So
Oh, wait.
charge,
Conservation, charge, and
strangeness.
strangeness.
You said baryon number. You missed one.
Wait,
It's
what? I said charge, strangeness, and momentum?
momentum is also
No,
conserved,
no.
but I'll just put it here. We usually ignore
What?
momentum in quantum mechanics for your level because it's rather difficult to actually treat momentum in a quantum mechanical fashion.
Hmm.
Okay,
Wait.
so baryon number.
Strangeness. Oh, it's a
Okay, it's also another kind of number.
Meson number.
No, the other one, lepton number.
Lepton?
Hmm.
Oh, yeah,
Now,
lepton, not
now,
meson. What the?
all right, lepton numbers though. I think I'll just go through this. Lepton numbers again. You do not consider all leptons the same. There's the electron lepton number. There's
Mhm.
the muon. There's the muon lepton number, and then there's the tau lepton number. In other words, your electron I'm just gonna say electron number. Your electron numbers must be conserved. Your muon numbers must be conserved, and your tau numbers must also be conserved. Okay,
Mhm.
so going back here, so we have one, two, three, four, five, six possible. Well, let's just say four possible conservation laws. Strangeness is not actually conserved.
Yeah.
Not in weak interaction, right?
Mhm.
Okay. So, um, which of these would you definitely test? So that's the thing here. Once you've identified these four,
Strangeness.
which one would you definitely test for? You can do strangeness because you see a
Oh, not
strange
strange.
part, right?
Wait. Yeah.
Mm-hmm.
Oh, yeah, 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 okay.
Okay. But
Wait,
here's the
are
thing.
you sure strangeness is not strangeness is conserved here?
Uh-huh, correct. Strangeness is conserved, right?
Mhm.
Uh,
Mhm.
conserved here. Why is it conserved? Because is it a weak
Because
or
it's a S and an anti-S.
okay? Is this weak or strong interaction?
You said it's not weak, so it's strong.
Strong. Okay. This is definitely strong interaction because strangeness was conserved, right? How about
Hmm.
charge? Is charge conserved?
Yes. No. Wait. Down.
Negative one third. Then
Mm,
anti-up is
so negative one.
this is negative
No.
one. Yeah, that's correct. That's negative one in charge. Proton would
Yeah.
be well, proton, we don't even need to think
One.
about that. It's one. So overall is zero, right? How about here?
But the
Over
bottom is negative one third.
okay. This is negative one third, correct? And then strange or anti-strange.
So it's plus two thirds. So it's one third.
Uh-uh.
So it's not
So
considered.
so this is
Wait.
one actually it is because remember that down is one third and the strange is also one third because it's anti-strange, it's negative. So what's the overall charge here? Zero, right?
Oh, I thought it became two thirds for because it
Mm-hmm.
was positive now.
Yeah.
Okay,
How
okay.
about here? Is this conserved? Up, down,
Yes.
strange. Also zero, right? So
Mm-hmm.
charge is conserved.
Considered. Mm-hmm.
Okay. Conserved. Okay, let's take a
Baryon
look.
number.
Okay. So we don't need lepton numbers. We need baryon number, right? So also
Mm-hmm.
conserved. So how would you answer this to get your 3 marks? Charge, you actually have to do the math a little bit like what we've done here. Okay. So what you can
Mm-hmm.
say here, and I'll move it over to the side. What you can probably say here is um, total charge before collision or before interaction
Mm-hmm.
is negative negative one plus 1, and that's equal to 0. Then, which is also equal to, after collision is definitely 0, right? Collision equals 0. So this means charge conserved. So you see what I'm doing? I'm just writing what we said, how we did the math. Charge is conserved. Now you can
Mm-hmm.
do the same thing for the other two. So this gets 1
Mm-hmm.
mark already. So same for the others. Okay. For
Yeah.
baryon number and strangeness. Okay. Okay. There.
Mm-hmm.
All right. So that would be how you get your marks there. Good. Uh, Before that though, I want to see what the mark scheme says, just to be sure. And that's the last question from the paper 2 we're doing. So I have another paper 2 ready. Okay.
Mm-hmm. Wait.
Let me just see. Okay. So in this case,
Wait.
how you get your 3
Uh.
marks would be you list your 3 conservation laws. That's the first mark. And then you show how it's conserved. That's another mark. And if you're able to do it for all 3, then that's your third mark. That's according to mark scheme. Okay. So in
Mm-hmm.
other words, the safest way to do this is to actually explain all the 3 possible conservation laws with the math. Okay.
Mm-hmm.
Okay.
Yeah.
All right.
Wait.
Question?
I wanted to do this one paper two question on like hitting the ball over a net
Oh, that question. All right.
again,
All right.
or like more of those.
Okay. Okay. Let me just see first. I know that's not it. Oh, not that last one. Hold on. Let me check. Okay. Actually, you know what? A lot of questions about mechanics still involves projectile motion. So, okay, this is the actual question from the one you said. And on the past paper that I have for you, there's a very similar question. You want to do this first or you want to go to that question?
This one.
This one first, all right? Okay.
Oh.
So, okay, let's see if you remember. How would you solve for the time it takes to go down and reach the table?
Oh. So that's vertical that we're talking about,
Yes.
right?
Mm-hmm.
Okay. So you, we don't need. We just look at the Suvat equation.
Yeah, exactly. So let's
Uh,
identify your suvats, right?
mhm.
S U
A is
V A
9.1.
T. I'll just use negative G for now. So that's 9.81, right? How about
S
S?
is minus 20, 0.24,
All right, correct. U is
0.
0 because vertical, correct. V, you
Mm-hmm.
don't know.
Unknown.
Time, you also don't know,
T,
right?
yes.
Okay. In this case, we want to know what the time taken for the ball to reach the surface. It should be around 0.2. So, which formula is the best one to use? Data booklet.
SU8.
What's the
Oh, data booklet. The second one.
Okay, data booklet, second one. Let me just copy the relevant equations. Right, so it is the second one. S equals ut plus 1 half at squared.
Mm-hmm.
Okay, yeah, that's it. That's how you do it. Make sure you do the math correct and you're safe. Yeah, so in this case, let's just put that in blue. So here we have S equals ut plus 1 half at squared uh, from here. Okay. All right.
Mm-hmm.
No need to solve. As long as you're able to identify your equations, we're good. Okay.
Oh,
For now,
okay.
at least for now, because you've done this before. All right. Next question. Sketch on the axes. Let's get the question first. Okay. Okay. So here we go. So you sketch on the axes a graph. showing the variation with time of the vertical component of the velocity v of the ball until it reaches the table surface. Take g to be equal to positive 10. So which equation, again, we go
Mhm.
to Suvat. Which equation is best? Or in fact, you don't even need
Um,
Suvat.
yes. Until the ball reaches the table surface. So at 2 is
Mm-hmm.
where the line should end.
All right. Here, v equals 2, right? So how about the time? What time
Oh,
do
in
we
zero
need?
point 0.2.
zero
zero
point
point 0.2
2.
it should end. But I'm not sure if it's 2. Is it? Wait, let me
Ah,
look at the
okay.
booklet.
Okay. It's still here. We're looking
Could I
for,
just say it's 2 and 0.2?
yeah, it is. Okay. And then how would the graph
It's
look
just a
like?
straight line.
Straight line
Straight.
from, well, okay, I'm going to try to make that a straight line. Let's try that. Yay, straight line.
Is it? No. No. It goes like, no. It goes like, you know what I mean.
I don't know what you mean.
Okay. It's high slope and then the slope like peaks, like plateaus.
Actually, this is already correct, CJ.
So that is, oh.
Yeah, this is
No, is that
correct.
acceleration I'm talking about?
Yeah. No, the one you're talking about,
No.
the one that looks like this, right? This
Yeah,
is
what about the other way?
time. This is time and displacement.
Hmm.
Okay. This is what it looks like. Uh, for again, this is time and displacement, but velocity time would be a straight line. Why? Because remember
Okay.
that v equals u plus at. Your u is
Yeah.
0, right? So remember that at t equals 0, v equals u. That's why we have this point here.
Mhm.
Okay.
Would acceleration be 2 going straight down to, if this was horizontal, I mean.
Okay. So, all right, I'll just finish this one. A GT now,
Sorry.
right? Okay. So back to your question. So what if the acceleration was 0, right? Then yes, it would look like that.
Mhm.
If the acceleration was 0, or as long as it's a horizontal line, that's gonna be okay. Okay.
Okay.
All right. Uh, Next one. This net. Okay, so let's go to the question on where the net is. So, uh, let's go to the next bit here. All right, I haven't shared this new link with you yet. Hold on. I'll just move this around and then there. So you have a net on the table. It's stretched across the middle. The table has a length of 2.74 meters and the length net has a height of 15. Show that the ball will go over the net. Again, what's the key uh what's the key idea you need here?
Mm. Now do I do horizontal?
Correct. You do horizontal.
And I have to make it, I find the T, right?
Uh-huh. Correct. So I'll just write here first. So you find something from the horizontal, and then you find time, and then you go vertical, right?
Mhm.
Okay. So what is the thing you want to do for the horizontal bit?
Focus on the 2.74,
Mm-hmm.
the initial height of the hit. No, I want, no, that's vertical. 2.74 is
Okay.
S.
Not quite.
Yeah, never mind.
It's not
Oh,
2.74.
half,
Remember,
half of
half of it,
2.74.
right? So S would be half of that. So I'll just write 2.74 over 2, right? So calculator, what would that give us? 2.74.
1.37.
Okay, 1.37. Okay, so we got our
Mhm.
S. Do we know our U? Do you know our V, your
0.
A, and your T? Okay, horizontally, we never assume that U is 0.
Okay.
And again, the assumption for horizontal motion is acceleration is 0 in horizontal motion.
Hmm.
Okay, so
Okay.
similarly in S U V A T, what would be 0 a lot of the time here in vertical? Well, none of them could be 0. There's a possibility that it's not 0, but the acceleration is always equal to g here. Okay, so that's the
Hmm.
only difference. All right, carrying on. Uh,
We know T,
do we know T?
right?
I I don't think so. I don't think we know T.
Oh, well, not at the same time. Okay.
Mhm. Okay, CJ. Okay, let me rescue you now. You're supposed to actually go the other way. You start from
Okay.
vertical, and then you work on the horizontal. It's gonna be
I
easier.
thought we did vertical.
Mhm. So the vertical displacement would be it's 15.
Minus 0.24.
Okay, so 0
Oh,
minus 0.24, correct? But that's not the actual answer. Remember, you want to clear the net, right?
oh. Um, 0.24 minus 50, 0.15. No? Yes?
Yes, it is. And that's equal to
0.09.
0.09. Okay, so that's vertical displacement, 0.09. You know you do, right?
Mm,
Mm-hmm.
0.
0. You don't know V and you don't know
Mm-hmm.
T. But we're looking
T.
for time, so, oh, sorry, not 0, unknown, right? You're looking for time, so that means you can use a suvat to find time, right?
Mm,
Okay, I'll go for
the
which one's the best.
second equation again.
Okay, so S
No. Yes.
equals ut plus 1 half at squared, right?
Mm-hmm.
Okay, right. So, okay, let's treat downwards as positive now to make it easier to just solve, right? So our u was 0, so that's gonna be 0, right? So S equals um
0.09. No?
okay, your S is 0.09, correct? 0.09, correct? And then find T from here, right?
Mm-hmm.
Mm-hmm.
I got 0.135.
Okay. So let me just calculate that. 0.135, right?
Mm-hmm.
Minus 2 divided by 9.81. There's that. Then take the square root. Did you take the square root?
Yeah.
Yes. All right, correct. So our time here is 0.135 seconds. Okay. So then we use that time into the horizontal bit. How far forward will it travel in 0.135 seconds?
Mm-hmm.
Mhm.
Mm. What? So for the horizontal time is 0.135.
Right. So this is so if we put that here, that's equal to 0.135, right?
Mm-hmm.
Okay.
Yeah.
Okay. Um hold on. Is there some, I think we're missing some information because otherwise because it's possible either way. Oh, we did miss some information.
Oh, we
You
have the velocity.
we have the initial velocity horizontal 12, right? So there, we
Mm-hmm.
missed that, so that should be 12.
Also, aren't
Okay.
we looking for S? No,
Yes,
we're looking.
we should be looking for S
Okay.
and then compare that to this. Okay. So
No, wait, are we?
Okay, we don't know
Looking
that,
at the t,
but must
the
compare
t is less.
uh, to.
Is it if the t is less than 0.135? That's bad.
Mhm. Now there are two way, this we're actually doing it the other approach. Last time we did horizontal time vertical. This time we're doing the other way around. We go from vertical, you get the time, and then find the horizontal displacement.
Mm-hmm.
Okay. So in this case, we will find that horizontal displacement and then compare it to the actual distance it travel, the actual distance to the net. So from here, S, what's the best equation?
S S U T S equals UT.
Well, if we just complete that, we get that, but that's zero, right?
Mm-hmm.
Okay, so S equals UT. So it's going to be 12 times 0.135. So what's that going to give us?
1.62. Wait, 12 times 0. Yeah, 1.62.
1.62 meters, right? If we compare that to the 2.74 over 2, or our what was our value again? 2.74 divided by 2 is 1.37, right? Meters.
Mm-hmm.
So in other words, what does this mean? It traveled farther than it had to. So that's our interpretation here. So the ball traveled farther, traveled farther than the net, right?
So
That
therefore it goes over.
so it goes over. So there. So that's the first. That's the second way to solve it. You start from the horizontal, from the vertical. You get the time, then use that time to see how much it actually travels compared to 1.37. Okay.
Mm-hmm.
The thing we did last time is just we started with the horizontal and found out the
Mm-hmm.
time it must travel, and then use that time to see how far it goes. If it goes if it goes below zero, above 0.09, it will not clear the net. Okay.
Mm-hmm.
All right. So either way, that should be fine. Let's go to the next question. Ah, D. So recapping this, where is it? Okay, there. So this time you have the ball bouncing off and then reaching a height of 0.18 meters above the table with a new horizontal speed of 10.5 meters per second after the bounce. The mass of the ball is 2.7 grams. What's the kinetic energy of the ball immediately after the bounce?
So 1/2 mv squared.
Mm-hmm.
EK equals 1/2 mv squared, which
Mm-hmm.
1/2 times 0.0027
Mm-hmm.
times
Okay, hold on. I'm missing a zero there. Times. Uh,
10.5 squared.
okay.
Uh, hmm, I'm missing something.
You're missing something. Remember,
Yeah.
energy formulas or energy problems are best solved by drawing first, right? So draw
Yeah.
first. So what happens here? There's your ball. And then you go basically like that, right?
Mm-hmm.
Okay. So what is again, what you need to do here is to find both kinetic energy and GPE in both cases.
Mm-hmm.
What's the GPE here?
Yeah. MGH, which is 0.0027
Mm-hmm.
times
G is 9.81.
9.1
What's the height right
times
here?
0.1,
No,
0.18.
no, this is the 0.18 because it bounces off first, right?
Yeah.
Okay. So how about here? What's the height here?
Zero. The
0.
height on the left is 0.
Okay,
Yeah.
on the left is 0, then on the right is 0.027
0.1.
times 9.81 times 0.18. Okay, all right. How about the
Mm-hmm.
kinetic energy here on both sides? Okay, here, let's take a look here. Where is this? Is this at the beginning or at the end? Just-
Beginning.
Okay, all right.
Wait.
Correct.
No, no, no. No. Oh, wait. It is correct, but I want to look at it.
Only one. It is correct, but
It's
it's
on the
applicable on
peak.
only one. Yes, this is your
It
10.5.
reaches top speed at the peak. Yeah.
Okay, so in other words, this is where you put your kinetic energy, right? 1/2 times the mass, 0.027 times the uh height, kinetic energy. Sorry, so times the speed, 10.5 squared, right?
Mm-hmm.
How about here? Think about it this way. Even though it's moving that way, it's also moving up. So basically, its kinetic energy is not just all horizontal, so to speak. Okay, even though that's wrong to say, okay, the kinetic energy here is gonna be bigger because of the fact that it's got a vertical and horizontal component to the velocity, right? So in this case, it's
Yeah.
moving at the speed v. But here's the thing: you're not actually being asked to find the kinetic energy at the speed. You're asked to find the kinetic energy. So this is already unknown. Okay. So what do you do now?
Mm-hmm.
What do you do now? Because it's about energy, we use conservation.
Yeah.
Okay. So that's gonna
Uh,
be 0. Okay. So conservation
yeah, that
means
does.
conservation means sum
Both
of,
sides.
yeah, both sides, and then you add up the energies on both sides. So this is gonna be Ke. We don't know, right? On the right side.
Yeah.
Okay. How
Oh,
about
so
on the left
KE
side?
equals you add both the right because
Mm-hmm.
the GP on the left is 0.
Mm-hmm.
KE plus GPE
Plus 0 here.
is KE on the left.
Yeah. Let's put left
Uh,
and then right, right? GPE
mhm.
left, right, right. So in other words, you know that that's 0 already, and we're looking for this. You can already go ahead straight away solve for it. So this is going to be
Mhm.
Ke on the left will be equal to this 1/2 times 0.027 times 10, right? 0.5.
Mhm.
10.5 plus 0.027 times 9.81 times uh
0.18.
0.18. Okay, right. So solve and then find the answer.
I got um 0.154.
Mm-hmm. 0.154.
154.
154.
Wait. Mm. Here, if I put it in parentheses, I get a different answer. If I
Mm-hmm.
put the number being squared,
Mm-hmm.
so I got 149. 0.149. Wait, no, 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 I'm tripping. No, I didn't get a different answer. Is it not 0.154?
No, it's not. I want to see the mark scheme. I'm a bit lazy with the actual calculations. All right, let me just see. Uh, what answer did I get? Okay, I got a slightly larger answer. Just a slightly larger answer than it should be.
What was it?
Okay, the marking scheme says the answer is 0.15 joules in this case. But
0.15.
mhm.
Okay.
So in this case, kinetic energy equals 0.15 joules. Okay. Now, the reason, let's see if that's correct. I'm gonna do the calculation here. 10.5 divided by 2 is that. Then plus 9.81 times 0.18. That's that. Then multiply the whole thing by 0.027. Yeah, that's the answer I get, 0.189. Why is the answer 0.15? Let's see if there's a difference between my method. That's correct. That's correct. That's correct. That's correct. Uh, oh, sorry. I think I know why. I'm missing a zero in the numbers I wrote. Right.
So
There we
that
go.
is.
Yeah, this is my mistake. Sorry about that. Yeah, we're missing a zero. Yeah. Now that we spotted the zero mistake, should still be okay. Answer's still gonna give you the same. Okay. All right. Ah. All right. Last one. This one is about the collision. Uh, so we're talking momentum, right?
Mhm.
Okay. So let's go here.
Oh,
Okay. Here we
is
go.
this the how many hours are left? Is it this last hour?
Yeah, this is our last hour already.
Okay.
All right. But anyway, we can go fast. All right. Last one. How do we do this again? Conservation of. Sorry, not conservation of momentum, but using the formula for momentum and force, right?
Mhm.
Okay. And of course, it says
Um,
elastic
yeah.
collision. Assume that the collision is elastic, so you have to draw the that bit. So that's gonna be exactly the same, yeah.
Mhm.
Now, remember what's force equal to? You said it last time.
MV over T.
M, not V, but delta
V.
V. Yeah,
Yes.
delta V over T. All right. So in this case, the mass is given 0.0027, right? Am I right again? I want to make sure I didn't miss a zero. Okay, that's correct now. 0.0027. What's your change in the velocity? And what's your time?
Um,
The
change of
time?
velocity is zero, isn't it?
No, it's not zero. The time's still there. Zero
Minus
point.
10.5.
No.
No, that's the direction.
Mm-hmm. Remember?
Velocity is a vector. Oh,
Yes.
oh, oh,
Yes. Yes.
oh, oh. Minus 10.5 the other direction.
Okay. So the other one is going to be 10.5 minus negative
10 point
10.5.
negative 10. Yeah.
Okay. So, okay. So that's how you would solve. Again, reminder for momentum problems. Always do this. Always remember the delta V. And then always
Hmm.
remember that one of them is negative.
Hmm.
Okay?
I keep forgetting it. I thought it was
Yeah.
speed.
Yeah. Again, if you can remember, what's the shortcut? Shortcut.
And
If this was an elastic collision, for elastic collisions,
it's just M. No.
okay, delta V is equal to 2V. Sorry, not that. Yeah. So let's put absolute values. So the absolute value of the change in the velocity is the same as saying twice the velocity. Okay.
Hmm.
So in this
Is this
case,
inelastic?
elastic only. Elastic only. For inelastic, this won't work. You have to
Yeah.
use this technique for inelastic. Okay.
Hmm.
But this can be used for elastic.
Hmm.
Right. Okay. So that's done on that problem. So yeah, the next bit here is gonna be about stars. So we're done with this problem. Let's move on to the second not problem. We're done with that paper. Let's move on to the second paper. And like I said, very similar question, right? I'll copy the question first. So instead of a ping pong ball, you now have a football.
Hmm.
Okay. I think I'll just place it right here on the next one. There we go. So you have a football player who's kicked a stationary ball with a given mass towards the wall like this. The initial speed of the ball after the kick is 19 meters per second, and the ball doesn't rotate. Air resistance is negligible, there's no wind. So if the player's foot is in contact with the ball for 55 milliseconds, calculate the average force that acts on the ball due to the football player's kick.
Mhm.
Okay, so
Uh, so we're finding F.
correct, you're finding F. You're given time and you're given
Oh,
speeds.
so
Yeah,
it's the second equation of 2.4.
2.4 second equation, which was
F
uh
equals the one we just used.
yes. So okay, I'll just
F
write that down
equals
straight away.
M
So we use
delta
use
V.
force equals delta P over delta T, and that's M delta V over delta T. Correct. So what's the
Yes.
mass?
And
What's the delta T, and what's the V?
M
Mm-hmm.
is 0.45.
Mm-hmm.
Delta V is like 19 minus 0.
19
No.
minus 0. Correct, because it was at rest, right?
Yeah.
Stationary. So 0. Correct. How about the time? It's given 55 milliseconds. So that's going to be 55 times 10 to the minus 3.
Mm-hmm.
Okay. So from here, calculate. So what's the force?
Oh, this is one mark. How is this 2 marks though? There must be like a catch though.
Let me check the mark scheme for how we get the 2 marks. Otherwise, I think it's the solution, or at
F
least
is
get,
155
yeah. All right, you get 2 marks for finding either the delta P
or
value or the
160.
acceleration.
Hmm.
Okay, but either way, correct. 160
160.
newtons. Yes.
Hmm.
So that's,
Is it easier to find P or A?
in my opinion, given this kind of data like this, it's easier to use this if you're given
Hmm.
masses and speeds. However, you can still also find the acceleration if you use 19 here, and then you use this time, you can find the acceleration, right? 19 meters per second by and minus 0 by 55. Then you multiply that by the mass, so gives you the force. But
Oh, because
in other words, it doesn't
unit stuff.
matter. Yeah, because of units. So in other words, it doesn't matter which
Yeah.
approach you use. As long as you get to this
Wait.
final version of the formula, it should be fine.
So you do 19 times 55, and
Mm-hmm.
it equals the acceleration because m per m over
Yes,
s
yes. So the
squared.
acceleration would be 19 over 55 times 10 to the minus 3. Then you
Mm-hmm.
multiply that acceleration by the mass. Okay.
Mm-hmm.
So okay, so I'm gonna do it. I think that's done for that. Okay, so let's go to B. The ball leaves the. Okay, you still can refer to the diagram here. So the ball leaves the ground at an angle of 22 degrees. The horizontal distance that from the initial position of the edge of the ball to the wall is 11 meters. Calculate the time given at the time taken for the ball to reach the wall. This is relatively easy, but um you need some trigonometry here.
Mm-hmm. Um, hmm. Okay.
Okay,
Well, I'll draw it out first.
okay, okay. Let me
Okay.
just.
So there's a 90-degree angle and there's a 22.
Uh huh.
The horizontal distance between
Mm-hmm.
initial. Okay. For the ball to reach the wall. Hmm. Okay. So we need to find the hypotenuse,
The
right?
hypotenuse. Okay.
Can I use sine rule, please?
You can. You can. Again, if you can use the shortcuts from trigonometry, go ahead. No one's gonna stop you. It's still the same anyway.
Okay.
Okay. And that gives me an idea. I wanna do what you just said. Use the sine rule to solve for this, right?
Mm-hmm.
Mm-hmm.
I got 11.9 for the
Il
hypotenuse.
Okay, hypotenuse is 11.9. Hold on, hold on. Not quite. It's not 11.9. The hypotenuse isn't 11.9.
Hmm.
I'll
What
give you
is
a
it?
clue. I'll give you a clue. Remember that the velocity on the problem is the initial speed after the kick. So in other words, we're looking at that angled kick already. So the
Mm-hmm.
19 is already actually this angled kick or this angled velocity. So let's put that
Mm-hmm.
there. This is actually already our 19 meters per second. Going that way. Okay. So having said that, yes, you do need the hypotenuse, but you don't need to find it. It's actually already your 19. What do you need to find?
Yeah.
What do you need
The
to
time.
find? And how do you
No.
find the time? You need to find this distance,
The
this speed, right?
distance.
You need to find the speed,
Oh.
Vx. That's V1, right? So what's Vx equal
Mm-hmm.
to?
Okay. It's
Uh-huh.
that thing where you do like 19, like sine 22 or something.
Right. Okay.
Am I tripping? Or...
You're correct. You're correct.
Wait, let me look at it one more time. Yeah. AV. No. AV. The what's it called? The vertical is sine. The horizontal is cosine.
Cosine, correct.
19 cosine 22, which is 17.6.
Okay. Times,
Right?
what's the velocity again?
19.
19. Okay. So that's, either way, that's correct. So you take the cosine of 22 degrees and multiply that by 19, you get to 17.6, right? So let's put
No,
that
that's the
in here.
velocity.
So Vx, let's label that. Okay. Uh,
Hmm.
so 19 cosine of 22 degrees, and that gives you 17.6 meters per second. Okay, so how about the time it takes to move for the ball to reach the wall? So
0.625.
how'd you get that?
Distance over speed.
Distance over speed, correct. The distance is 11 meters, right?
Hmm.
And then the speed is there, that's 17.6. Okay, so I'll just finish this. So, mhm. Okay, so what's the time you got again? Sorry, yeah, the time here is, so the time here is 0.62 seconds. Okay, all right. Let's go to the next bit. Okay, the top of the wall is 2.4 meters above the ground. Deduce whether the ball will hit the wall. So you see, this is really similar to the other one. It's just a different context.
Hmm.
Hmm.
I like this context more because it's something I'm actually interested about.
Yeah. All right. Yeah. Yeah. Football.
Hmm.
All right. So this is 3 marks. So will the ball hit the wall or not?
Um, that's 3 marks. Okay.
Hmm.
Top of the wall. Okay,
So
so
it's
we find the
Go ahead.
no. Do we find the other side, like the vertical? We found the
Yes. Yes, that's right.
hypotenuse and I don't know what it's called.
You're right. You're
The
right. You
bottom
have
line. Now we need to find
uh
the
you need
vertical.
to correct, correct. So what's Vy?
Mm-hmm. By. Should I use Pythagoras?
You can, or you can use you can use the other trigonometric thing. You
Cosine
already
law?
that you
Oh, sorry.
use. Here's the idea. You already used cosine in part one. So what do you do now in part two? You're gonna use
Sine.
sine.
Oh, 19 sine.
Okay.
I don't know the distance. 19 sine 20.
Okay. So remember the angle was
19 sine
22 degrees.
90. 90. Wait, 19.
Okay. Let's go back to the diagram right here. Remember the angle is 22 degrees. You're looking for Vy,
Mm-hmm.
right? You know that this is 19, this is 22 degrees, and that's Vy. So what's Vy equal to?
19 sine
19
22.
sine 22 degrees, right? Okay, then let's just put that in, whatever the value is.
711.
Ah, interesting value.
Oh, 712. 7.12.
Okay, hold on.
Rounded.
22, take the sine of that, and times 19. Yeah, it is an interesting. That's 7.1. Well, I just want to write that whole number because it looks so amazing. Wait, even the
Is it
next
unusual?
it's unusual because of the pattern. It's not unusual for anything else. But I'm gonna write the next two numbers. So
Yeah.
all right.
And
Uh,
then there's another 7.
yeah, and then there's another seven
Yeah.
at the end. All right, but yeah, after that doesn't really do much anymore. All right. So carrying
Yeah.
on, what's the next step? We found your Vy. What do you do?
Oh, we found our. We find the time.
Well, you know the time, right?
Oh,
Okay.
yeah, we do. The distance.
Okay, you find the distance. So in this case, s, right?
Mm-hmm.
Okay. So what are we gonna use? Which formula are you gonna use? Which Suvat equation?
So we have time, we have speed, we have its initial speed.
Mm-hmm. This is already the initial, right?
Mm-hmm.
So I'll just label that. This is
We have
initial.
its final as well, right?
What's its final? At the top.
0.
Okay. So U is equal to this 7.117, right? 52. I'll just put it
I
there. And
think
then,
we use the third one. V squared equals U squared plus 2AS. No, we don't have
okay.
A. Never mind.
You do have a, remember, vertical.
Oh, yeah. Then is it the unusual one that we chose? Could we have done the second one then?
No, it's not really unusual because remember, your acceleration always has one of two values, depending on whether it's horizontal or vertical. If it's horizontal,
Mm-hmm.
acceleration's automatically zero for projectile motion. If it's
Mm-hmm.
vertical, for projectile motion, it's automatically 9.81, automatically
Mm-hmm.
g. Okay, so in this case, let's put that in negative 9.81. In this case, we don't know t, we don't know s, we don't know t, but we only really need to find s, right?
Mm-hmm.
Okay, so what's the height it reaches? So from here,
Um,
which formula to use?
you said the third one, right?
Mm-hmm. You said the third
Yes.
one, so which is
So,
v squared
um,
equals
U
u
squared plus
plus 2as.
2AS.
So our v here is 0, right?
Mm-hmm.
Then this is gonna be 7.1175 squared plus 2 times a negative 9.81. Let's move that a bit. And then your s is, we're looking for it, right? So finally, what's s equal to?
Wait, 7. Why is this 7.12 squared again?
Because
Oh,
because
that's the
our
vertical.
yeah, that's
Yeah.
the vertical, right?
hmm Plus 2. Plus. Okay. Uh,
Okay, I'll just put that in
we
a
don't need
box.
t for this one, right? We
Nope,
just
we
want
don't.
d.
Yes, we don't need t
Yes.
because it's already been solved, right?
Yes. Oh, I could just use um the polysymbols on the calculator.
Mm-hmm.
No, I can't. Mhm. I got negative 2.6, negative 2.58.
Okay, actually it should be positive, but yeah, 2.58 is correct. Okay, why is it positive? Because remember, here your acceleration is negative, so negative
Oh,
that.
right. I didn't put negative.
Yeah, but in this case, it doesn't matter. In this case,
Wait, I
you
didn't even put the acceleration. I think that's wrong. Wait, my bad.
okay?
Um, um, is it 0.26?
0.26. How do you get 0.26?
Wait, no, I'm.
Look, I have a
Oh, I
question.
did do the acceleration.
Did you
I
square?
did do the
Oh, you
acceleration.
already did. Okay, so good. You already had the
But
answer actually. The 2.58 is correct.
I, yeah, I just forgot I put it down.
Hmm. So remember, after that, compare. The top of the wall is 2.4 meters. Your S is 2.58. So does it clear the wall?
No, it won't. It clears the wall, yes,
It clears the wall.
but it
So
will not hit the wall.
not hit wall. Okay, done. So that's your third mark, the deduction, the final deduction. So it will not hit the wall. All right. The next question is about air resistance.
Wait, we have a meeting tomorrow, right?
Yeah, we do. I gotta check the
Okay.
time though. I think it's at normal time, but only an hour, I think.
hmm
Then after that, we're done for physics.
Yeah, wait, when do I cancel exactly?
Up to you, but I think you can start canceling after tomorrow. Unless you want to
Yeah,
study
oh, okay.
math.
Math?
Yeah.
Do you know the Alex placement test?
Alex placement test. First time I've heard about it.
Alex, like not Alex, but like Aleks.
Yeah. Yeah, still the first time
Hmm.
I've heard about it. I can search it
Okay.
now. Alex placement. Oh, okay. Oh, it's for math readiness. Okay, got it. So, yeah.
Mhm.
I can try to see what how you can study for that later on, but let's
Mhm.
see. All right, let's go back to the
Okay.
question. Practice air resistance affects the ball. Outline the effect of air resistance, that air resistance has on the vertical acceleration of the ball. Take the direction of acceleration due to gravity to be positive. So, what does air resistance do to the acceleration?
Uh, hmm, uh, it, it doesn't because the acceleration will always be g if it's vertical.
No, remember that that idea is true only for instances where you ignore air resistance. But in this problem, you cannot ignore air resistance anymore. In this part,
Hmm.
at least.
Then wouldn't uh,
I'm gonna give you a
I'd
clue.
say
Give
terminal
you
velocity stuff.
terminal velocity should kind of work. Yeah, should kind of work.
Oh,
Okay,
yeah,
I'll give you
as
a
it
clue.
reaches terminal velocity, acceleration
Acceleration
It's
will,
constant.
no,
Will
not quite.
decrease.
It will
Oh,
decrease, okay? Hold on. Let me see the actual answer.
won't it, won't it stop accelerating if it reaches terminal velocity?
It does. The acceleration becomes zero once you go to terminal velocity.
Hmm.
Uh, okay, I'm looking at the mark scheme. I don't think I can give you a mark for that. No marks.
Oh, I don't know.
The idea is correct though, I'll say that. Okay. All right. Okay, so here's the idea. Let's take a look at the ball, right? If it's going up, and then let's take a look at the ball when it's going down, right? So V going this way and V going this way. Which way is the force? How many forces are acting on the ball? Two, right? One is air resistance, the other one is the weight.
Mhm.
So in this case, which way is the weight directed?
Mhm.
The weight is always directed down, right?
Mhm.
How about the air resistance? And this is where you'll see the answer. Which way is
The
the air
resistance is up.
resistance? Up for which one? The one on the left or the one on the
Up
right?
for the wait, the left. Why? Oh, it goes up because the ball is thrown up.
Mm-hmm. So air resistance is
Wait,
this
if
way.
it's on the left, it's down
Okay, air resistance goes down. So, okay, so that's
on
air
the left.
resistance. And how
But
about
then air
here on the right?
resistance goes up.
Up here. Okay, correct. So what does this mean? This means that the resultant force here is bigger than the weight, right? So resultant force is
Doesn't air
large.
resistance always act against you
Against
whenever
the
you try
motion.
to go a certain direction?
Yes, exactly.
Against motion, yeah.
Exactly. So in this case, this is going to be
F1
bigger
moment.
than mg, right?
Hmm.
How about here? Your sum of forces here will be the other way, less than mg, always, right? So,
Hmm.
and remember, this is MA, so MA is less than mg, and here MA is less than mg. The other one's greater than. So the masses cancel out. So we're just left here with the acceleration is greater than g on this side, on the left side, and on the right side going down, the acceleration is less than g. So this is already your answer. Just say this in words. So from here, what happens? The
Oh, um, air resistance acts opposite to the motion.
Okay, so that's one mark already. So the air resistance, because it says the effect of air resistance right here, right? So air
Hmm.
resistance,
Leading to a
uh-huh,
decrease in acceleration.
a decreasing acceleration for where? Going up or going down?
Uh,
So air,
Both. No,
only one, only one. Air
going up.
resistance opposes motion. So okay, now I will say it like this. This part we agree on. Air resistance opposes motion, right? The next part
Hmm.
I'm gonna say here. So the ball, the ball's acceleration is less than g going up as it goes up.
Yeah.
Oh, sorry, not less than, greater than g, right?
Oh, yeah. But then it'll eventually be weaker than G.
Okay. So as it goes down, I'm just gonna put it here, goes down, right? It's less than g as it goes down. It's gonna be more than g
Mhm.
as it goes up. Okay. So one of these other two statements would give you your second mark. Goes up. Okay. So which statements would be worth one mark? It's gonna be, so the ball's acceleration. Okay. So this is one possible mark, or this is another possible mark. And then the second possible mark is this. right?
This is what.
So this is your first mark, and then this would
Mm-hmm.
be your other mark. Saying one of these. Either
Mm-hmm.
the acceleration is less than g as it goes down, or more than g as it goes up. Okay.
Mm-hmm.
All right. Uh, what's the next question? All right, let's go to the next question. Okay, last question on this topic. So this time the player kicks the ball again. Hold on. Let me move that. So the player kicks the ball again, and in doing so, the ball rolls along the ground without sliding. So the keyword here is without sliding, right? So this means it's just rolling with a horizontal velocity of 1.4 meters per second. The radius of the ball is given. Calculate the angular velocity of the ball. State an appropriate SI unit for your answer.
V R angular velocity. Oh, omega.
Mm-hmm. Okay, this omega is equal to
Because something v squared over r, something like that. Wait, I'll look at it.
mm-hmm, mm-hmm.
The
Uh,
v equals angular r.
yes,
Therefore,
that's better. You use that. So V equals
angular r.
omega R.
So omega equals v over r.
Yes,
Is this two marks or one mark?
that's just one mark.
One.
Yeah. So basically that's it,
Hmm.
right?
Hmm. Hmm. 1.4 over 0.11. Right.
1.4 over 0.11. Okay, I'll be honest with you. I'm feeling lazy right now. I'm a bit tired. I'm gonna just
Same.
check the
Yeah.
mark scheme here. Uh, so what's that answer? I just want to see what the final answer is before we say anything. So 1.4 by 0.11. Yeah, this is correct.
I'm just gonna say
Unit though.
SI unit. Is
Mm-hmm.
it not in speed? Is it not in fs minus one? I just need to know.
No,
It's not
because
in fs minus one.
angular, remember that angular should be in some angular measurement. So angular
Okay,
measurement.
I got this. I got this.
Okay.
Does it have M and an S in it or no?
It has S. I'll say that. It has S.
Okay. Is it in the formula booklet at all? This value.
No, it's not.
Is it theta S?
Close. You have the
Theta
percent.
S minus one.
You have the. No, it's not theta, but the
Oh,
S minus one is now correct. Okay, I'll tell you now, yeah? This is already correct.
okay. Yeah,
Okay.
because the
Why?
M cancel out.
Exactly. M's cancel out. Now,
Oh,
if you wanna, if you're not comfortable with not having that unit and you just have, you're not comfortable with just having 13 per second like that, right? It is,
mhm.
it, you can, I think, yeah, the Mars team allows this. That's 13 radians per second.
No, I'm never doing that. No.
Okay. So that's going to be 13 in radian per second. Okay. But the thing about the radian, it's not really a unit, it's more of a ratio between two lengths. So the radian itself doesn't actually
Mhm,
have a unit. Okay.
mhm.
Now,
Do you
uh,
think I can do all the calculations with degrees?
circular motion, we would rather avoid degrees. We want to do
Okay.
degrees for we're okay with degrees for everything else except
Okay.
topic 6. All right. Topic 6, you must
Mhm.
stick to radians. All right. All right. Okay, we have around 15-20 minutes. Okay, I'm gonna let you pick the topic. You want ideal gas laws, electricity, magnetism? waves, quantum mechanics, or energy production?
Mhm. Sorry.
Okay, so again, I'll let you choose the topic this time. Yeah. So we're done with topic one,
Oh, can
two,
we do astrophysics?
astrophysics. That means option. Okay, let
Yeah.
me open an option paper real quick. Uh, you know what? I'll do 2019 if you haven't done that yet. 2019. Oh, okay. I'll do a November paper to be safe. Hold on. Physics, physics, physics. Paper 3. Okay, here we go. Okay, mark scheme's ready. Let's just wait for the paper. All right. So while the paper is opening, let's think about this. Uh so you're okay. I think you're already okay with the data analysis section, right? And okay,
Hmm.
more or less.
Wait, maybe we could just spend the last few minutes in data analysis because astrophysics I could review on my own. But I
Yeah.
need to work on the skills maybe. Yeah.
Yeah. Okay, so we'll do that right now. Uh Data analysis. All right, so first of all, here's the first question. You're given immediately the graph. Okay, so there's an investigation by a student of the period of a simple pendulum varies with the maximum velocity of the pendulum's bob. Okay, maximum
Hmm.
speed. Okay, so basically it's by releasing the pendulum at different angles. So this is what we get. So why is it? So the first question here is, I think I'll copy all the questions first here. Do it like that. Okay. So suggest from this graph, okay, why is it unlikely that the relationship between T and V is linear? Why is it unlikely
Be-
that it's linear?
because there's because it does not go through the origin.
That's one. And then what
The
else?
other is that there's a not only is there a vertical error bar, but there's also a horizontal error bar.
Okay. Um, those are not gonna get marks in this case. The
Oh,
origin is not about being linear, but about being proportional. So
yeah.
let's note that there. Yeah. So origin. So proportional is
Oh,
going to
I can
origin.
see that it's not linear because it looks like there's like a little curve
Yeah, exactly. You can just
at
say that right away.
it looks
Proportional.
like there's a little curve starting at like
Mm-hmm.
2.15 or 115. I mean,
Okay, so correct. Passes through. Okay, I'll just note this down through the origin. Okay. Now the best answer here is the points seem to curve, right?
seriously?
Yeah, that's all you can
Why
say
would they
here.
put this in them? Okay.
The points seem to follow a curve. That's
Hmm.
one mark
Do I
already.
have to draw it out to prove what I mean?
No, no need. Unless you want to, but in these cases, we don't have to. Okay.
Hmm.
Now, another possible one, and this I think this would be more satisfying for you, is if you try to draw a straight line. I'll just demonstrate it right here. Oops. If you try to draw a straight line, you cannot pass through any of the error bars or all of the error bars, no matter what you do. You see?
That's true.
This, okay. So that's another more satisfying answer, IB wise. Okay. So
Hmm.
you can, so,
Wait,
but I would
can you draw a
pursue,
maximum line? on this?
A
A
maximum
max
line?
and a min?
You could, but that also means you need to have an average line. And the problem is, it's the
Mm,
average line that's actually the most useful out of the three. Because the
yeah.
average line will tell you whether you do have a linear correlation or not. Okay. So another one here, and I'll just note that here. Oops, I'm still on line mode. Hold on. Another one that you can do here is the points. Okay, a straight line cannot be drawn through all the air bars. Let's look. A straight line cannot pass through all error bars.
Hmm. Would that be better than say the points
Um,
seem to follow through?
the IB wise, I would suggest this IB wise, okay, because
Mm-hmm.
this is the safer answer. However, that doesn't mean that the this is incorrect. This is still correct. This is just safer.
Mm-hmm.
Okay. All right. Okay. Let's go to B. Okay. B, determine the fractional uncertainty of V when t is 2.115 seconds, correct to 1 sig fig.
Oh, I was just talking about this.
Mm-hmm.
Um, okay. So, can I look at the point? Oh, I see it.
Mm-hmm. Okay.
It's
2.1
um,
there.
it's 0.1 on the left, and on the right it's 0. No, it's 1.1 on the left, and it's 1.2 on the right. So
Okay.
it's 0.1 horizontally,
Okay. So
but
let's
vertically,
so but here's the thing, you only want the uncertainty in V. So do you actually want
oh,
the
no,
vertical? You don't, right? So
no,
delta V is equal to what? Just delta V.
1/10.
1 over 10. Is it? Let me double check.
I know.
Mm, so it's this guy. So okay, that's 5. So every 5 is 5 divisions. Okay, it's not 1 over 10. Okay,
Yeah.
it is 1 over 5. Okay,
Mm,
why is it 1 over 5? Because what you did here is you took this value and you read that as how this is 1.2, right?
yes,
1.20, and this was 1
1.1.
1.1, right? This length is 2 times the uncertainty.
Oh, yeah, it is.
Okay, so that length is 2 times the uncertainty. So the uncertainty must be half of that.
Yeah,
So
so it's 1.5. Okay.
0.05. Okay.
Mhm.
All right. So that's the uncertainty. The next part is, what is V? That's 1.15, right?
Mhm.
Okay. So what's delta V over V? Because fractional uncertainty, you need this. So what's delta V over V? Very straightforward. You just calculate that. Okay. Let me just see what the marking scheme says on how you can, what the actual answer is. Yep, this is correct. And then you need to calculate. So we cannot leave it like this. So if you calculate this, this gives us 0.04. Okay.
Wait,
Okay.
so 1/5? Delta V, yes, it's 0.05 because of the uncertainty.
Mm-hmm. Okay.
It's 1.15. Oh, that's the uncertainty you're finding.
Yeah. So
Oh,
this is
delta
just,
V over V.
yeah. So we already have our delta V, and then we can read your V. But since we're looking for fractional uncertainty, we need to divide one by the other. And that's what happened here. Okay. And then solve and
Mm,
whatever. And then it says correct number of sig figs. You have to stop at 4. The actual answer is 0.0143,
3, 5.
right?
Mm-hmm.
435. But because of sig figs, 1 sig fig, you have to stop at 4. Okay.
Mm-hmm.
Um, let's see. Okay. So we have the student now making a hypothesis that the relationship is like so. Let's put it on the next bit. Okay, between t and v is that t equals some value. I'm just waiting for the question to come out. Okay, there we go. Okay, so there, the student hypothesizes that the relationship between t and v is given by that equation, t equals a plus bv squared, where a and b are constants. To verify the hypothesis, a graph showing the variation of t with v squared is plotted as this. So we have the lines of best fit and the graph of the data. So determine b given the appropriate unit for b. Find b.
Mm, mm. So I find the proportion. No, it's not.
Mm-hmm. Now,
Okay.
okay. Here's the thing. Look at the equation. Is b your
Mm.
y-intercept or your slope?
My slow.
The slope.
My slope.
The slope. All right, it is the slope. Okay. So b is the slope. So how do you find the slope?
Um, rise over run.
Rise over run. Go ahead. Pick your 2 points for your rise and your run.
Okay, I'll pick the first and the last.
Okay. Always the best 2 points to pick.
So 2.105
Okay.
over 0.5.
2.105 over 0.5.
Wait, I'm tripping. No, that's not coordinate. Sorry,
Yeah.
sorry, sorry,
Well, yeah, that's fine. So
sorry.
you can still fix that, right?
Yeah.
So that's that. And then we need this one.
Uh, that's 2.155,
Okay. And then,
and then comma, 4.45.
yeah, 4.45.
No, 4.4. Sorry,
Okay,
4.4.
4.4. All right, 4.40. Right. So that's your B. That's the value. Let's
Mhm.
just find the final. Let's just find the value here. What is it?
Um, yeah, isn't it y2 minus y1?
Yeah. But here's the thing. It doesn't really matter which one is which, as long as if this is y2, this should be x2. Similarly,
Hmm.
if this were
Oh, it's the
y1,
same.
this should be x1. You cannot. You have to have them in the same order, but you can switch,
Right.
kind of switch the orders. Okay.
Mm-hmm.
But
Then
you
it's
can.
0.0128.
Mm-hmm,
So you can switch the order as long as you do it both sides.
mm-hmm,
So
right.
B equals 0.0128, and the unit is
Mm-hmm.
um okay,
So whatever
um
this unit,
m
whatever this
squared
value is, okay,
s minus 3.
is it?
No, no,
Okay, marking scheme. Let's take a look.
it's not. It's gonna be sad.
Oh, I think I'm looking at the wrong thing. Okay, here's the thing. I'm gonna. You're half right.
Hmm.
You're half right here.
It's over
Rem-
S though.
Remember, go back to the fact that when you do gradient, it's rise over run, so y over x, right? So what's the unit for your y? It's gonna be second.
S.
Then divide that by meters squared per second squared, right?
Oh.
So again, this value doesn't matter for us for right now. Just calculate that, right? But this part, once you have this, just move stuff around when you can. So this becomes s cubed per meter squared, right? And that,
Wait.
so
Really?
b is equal to
Oh
whatever
yeah, it
value.
does.
And yeah, so that's gonna be your final answer here. Uh,
Mm-hmm.
I wanna see what the three marks are. So first of all is, yeah, finding the gradient. The second mark is for having a value of the gradient between, this is your second mark, between this b equals 0.012. Mm-hmm.
Wait. Quick question.
Yep.
Is S on top S to the minus one
Mm-hmm.
over? Okay. Okay. So it's a
Okay.
minus minus minus. Like it's a negative subtracting a negative.
Yes.
So therefore it adds.
Mm-hmm. That's correct.
Okay.
Okay. So so the best possible answer here, I'm just gonna say 0.012. Okay. All right. So that's your B. All right. Last one for today. So you can take a rest, and so can I.
Mm-hmm.
Yeah, you need your rest because tomorrow, better to be well rested before an
It's an
exam.
afternoon. That's true.
So you can still stay late because you did say it's in the afternoon, but not too late, yeah?
Yeah.
All
True.
right. Last question for now. So you now are given the minimum and maximum lines for the gradient. So from there, you need to estimate, or yeah, you need to estimate, and boxes are gone. We ran out of boxes. All right, let's just base that. Ah, why did we run out of boxes? There we go. All right, so the lines of the minimum and maximum gradient are shown here. So again, from here, just estimate the absolute uncertainty in A. A, going back to the equation from earlier, A is your what? So if B was your gradient, right? If B was your gradient, what is A?
Y-intercept.
Y-intercept. All right, so go back to the graph, and here we go. What would be the absolute uncertainty in A? Estimate.
So we find the value of the. Okay. Okay. So we do 2.10005
Okay, 2.1005
minus
minus 5.
2.0095.
Uh-huh. 2.095. Correct. Okay. Then,
Uh, Subtract and then it equals 0.0055.
mm-hmm.
But oh wait, that's fine, right? Or does it want one sig fix?
Not quite. There's something missing here.
It
It's
is
not the sig figs.
absolute,
Uh,
absolute.
no. Remember again that remember, just like earlier, this is twice the uncertainty.
Divide by two.
Yeah. So divide that by 2. Right? So with that, final
Zero point
answer,
zero two seven five. 0.0275.
0.0275. But let's just round that up. So that's going to be 0.003.
0.003.
Okay. All right. It's absolute already. We don't need to find the fractional value. We don't need to find the value of t here. So we're good. That's good enough. Last thing before we end, I just want to look at the mark scheme. Yeah, we're good. We're all good here. Okay. Anyway, it's just
Yeah.
an estimate anyway, so you don't really have to have exact values for the actual answer because of the word estimate. Okay.
Mhm.
All right. So in fact, oh, okay, we're good. Uh, yeah, I think that's good enough. So there, that's good. Um, that's it for then. That's it for today then. So is you have anything else to ask before we end for today and you get your rest?
No, that's
No.
good.
All right. All right.
Yeah,
Good then. So we'll continue again tomorrow for I guess tomorrow we do paper two because that's no, what's on Thursday? Isn't it paper? It's paper two, right?
Thursday.
Paper one is tomorrow.
Thursday's paper 1 and 3.
Oh,
Oh,
yeah.
Thursday is tomorrow.
Yeah, Thursday's tomorrow, so paper one and three tomorrow. Then on Friday, paper two, right? So tomorrow on our
Hmm.
last meeting, we'll finish the paper two questions that we've been doing. Okay.
Hmm.
All right. So good luck tomorrow, and see you on the other side of the exam. All right. I
Okay.
wish you all the best. Then I'll
Thank you.
see you.
You
All right.
too.
All right. Have a good
You too.
evening.
See
Good
you,
night.
students. You too, students. Bye.
All right. Great. So that's the end of the lesson. So 2 hour stream today. Did anyone have a question? Not really. All right. So anyway, let's go back to the main board first. Okay, so again, as I've mentioned a few times, tomorrow would be the IB physics exams for papers one and three. Paper one is the multiple choice, and paper three is the data analysis and option paper. Now, for everyone taking the IB exams tomorrow, or even today, because the IB exam started today, whatever subjects you're taking, I wish you all good luck. If you're taking physics, I hope I have helped. So good luck. And well, if I did help, don't forget to like, share, and subscribe to the channel. Go to the social media platforms on Facebook, YouTube, TikTok, Instagram, and Twitch. Follow us there and watch for more live streams. So hopefully, again, we helped you guys. If you have been helped, please also spread the word. Okay. So with that, I bid you all a good afternoon, good evening, good night, good morning, good day, wherever you are in the world, and stay freaky, everyone. Have a good one.